Okay, hey Dynamics Lab, we're just here making another supplemental video, and this is really just a supplemental video to go along with the pre-lab for tomorrow's lab for titration of a weak base with a strong acid. First thing, I think I got that backwards on the title of the pre-lab. I think I put weak acid with a strong base. It doesn't really matter, so I think I messed that up. So more specifically, what we're doing this week is we're titrating a weak dibasic compound, sodium carbonate, with strong acid, HCl. So that's what we're doing. And this is actually the first in a series of labs that we're doing, acid-base and equilibrium chemistry combined, and also a buffer lab down the line. This is all really important stuff for biology, for geoenvironmental studies and chemistry. So these are really good labs. They're pretty complex. So all this is a supplement to the pre-lab. The calculations that you're doing in the post-lab, we'll talk more about those just in the lecture because I think it'll make more sense. In fact, I think what we'll do is maybe even do the calculations post-lab. I think will make the most sense rather than just try to make this a 45-minute long video. It'll be way too long for that. So this is a supplement to the pre-lab. So just so you know, some of the basic ideas of what we're doing is you're making a solution of sodium carbonate. Now sodium's a spectator ion, so we're just going to ignore that. And then we're titrating it with HCl. So you may have picked this up from reading the pre-lab, but there's actually two equilibria we're paying attention to here. So we're starting off with carbonate, from sodium carbonate. And when you titrate that with HCl, so the H plus comes from the HCl, you're actually setting up this equilibrium. And that's the first endpoint. So this is dibasic. So you neutralize the carbonate with hydrochloric acid, and you produce what's called the bicarbonate ion. So that's the first step. That's the first endpoint that you're going to do. So you're going to see two color changes today, or in lab. Then you take that bicarbonate and keep going. Then you go, once you're past the first endpoint, you continue the titration to the second endpoint. Whoops, that wasn't a very good arrow. And you make carbonic acid, H2CO3. And I believe if you read the procedure in the pre-lab, it gave you this as your net ionic equation for equation 1, and then asked you to do the net ionic equation for equation 2. So I think that's right. Now, we're not doing this next thing that I have labeled here in lab this week, but I think it's a good time to introduce it. Next week, we're actually going to stick a pH meter into the reaction mixture and monitor the pH. This week, we're calculating the pH rather than measuring the pH. I just want to show you what this looks like because I think it makes conceptual sense. So a titration curve is where you monitor the pH of something and the volume of whatever it is you're using to do the titration. So the titrate. So in this case, we're putting sodium carbonate in an Erlenmeyer flask and titrating it with HCl. So here's what it would look like, and I think this kind of makes sense. So sodium bicarbonate's a base, so it starts off at high pH. As you add HCl, the pH starts to drop. When you get close to this first equivalence point, when you get really close to it, also called endpoint, remember endpoint is the color change, equivalence point is when the moles are matched up. And ideally those are the same. So when you get close to the endpoint, boom, the pH really drops. Then if there's another endpoint, you keep titrating, it kind of plateaus off, and when you get close to the second endpoint, it drops off precipitously again. So this is what a titration curve would look like with a weak dibasic compound with a strong acid. And your two endpoints, if you've had calculus, are in theory the inflection points, if you remember that, of the curves. So now you're not doing this week. I thought this would make sense. So in the middle of the steep point is the theoretical equivalence point. So what you could do is this would be the pH at your first equivalence point, and that's, you can see that in your pre-lab, what we mean by that, your first endpoint, and this would be the pH at your second endpoint. So in lab today, the ultimate goal is to actually calculate these pHs, which is going to be kind of interesting to do. All right, So that's enough of that. The last thing I want to explain to you is kind of how we're collecting the data, so we can move over here. And I ask you to do a couple of things with the pre-lab. And I'm not going to give you all the answers here. So the first thing you're doing in the lab is you're actually preparing a standardized solution of sodium carbonate. It's a primary standard. It's very pure. It's very dry. It's really good for that. So you do the calculation. We're using a 25.00 milliliter volumetric flask. So that's 4 sig figs. So you should calculate how much mass of sodium carbonate you would need to make a 0.1 molar solution. Now when you do that, you actually go into the lab, go measure that mass, approximately, get as close as you can, and then you'll back calculate what is the molarity of that solution to 4 sig figs. So you'll have that, and it should be approximately 0.1. So if you get 0.09999, something, then you're good. If you get 300, then you did a calculation wrong, and you can figure that out later. Okay, the next thing we're doing in the lab is then you're titrating that sodium carbonate solution, which is now standardized. You know what its molarity is, 3 times with unstandardized HCl, which has about the same molarity. So you know the answer in the end should be about 0.1, but it's unstandardized. What I want to explain is how this data table is set up, and maybe you figured it out because in the lab manual, the instructor, Dr. Lacey, when he wrote this, said, copy this table down. So that's all I'm doing here, is just kind of show you how this works. Because we also did a titration earlier this semester, so this should be pretty straightforward. So you have 2 microburettes set up, one to dispense sodium carbonate and the other to dispense, or actually titrate, with the HCl. So you have 2 of those set up. Okay, so the first part of the data table is just for the dispensing of the sodium carbonate, and we're doing 3 different volumes, 1 mil, 1.15, 1.25 for your 3 trials. So these initial and final volumes are just your microburette readings. So if you start off with 0.00 as your initial volume, you put the meniscus the whole way at the top, you just push it down to 1.00 and go from there. Then if you just keep adding, then that would become your initial volume here, and you dispense down to 2.15 as best you can. Now of course you write in real data, just so you know how this is set up. Now the titration data, since there's 2 endpoints, we actually are going to record 2 sets of initial and final volume. So how you want to set this up is entirely up to you. With the way I did it, maybe this is going to be confusing. So you're just using VI, VF, V, or delta V. If you want to use delta V, that's perfectly fine. Okay, so you have 2 sets of those, VI, VF, delta V for the first equivalence point, VI, VF, delta V for the second equivalence point. And maybe that's all you need to set up this table. So I just use this notation. So you have the initial volume for the first equivalence point in milliliters. Fine, okay. Then you do the titration until you see the first color change, and you record the final volume of the first equivalence point in milliliters. Then you subtract those 2, and that will give you the volume it takes to get to the first equivalence point. And I think you can see where we're going with that. And I'm going to run out of space, but then you'd have another set of those data for the second equivalence points as well. So you'll have 2 sets of those. And I think that should be good to go. The last thing I want to show you is the basic calculation for how do you take this data and calculate the standardized molarity of the HCl. Now we've done that before. I don't think this is going to be too much of a problem, but just give me a second because I need to erase some of this information. In fact, I think I'm going to erase this table because this looks like a big mess. So if you need to kind of make your table now, that's fine. So when all is said and done, the next part of the lab is to calculate the molarity of the HCl. And you've done this before. So this is a titration calculation. And titration calculations all start off the same way. You start off with the molarity of your standard. So you know what this molarity is to 4 sig figs. You know what that is. And you multiply it by the volume. Now, technically, if you're going to multiply molarity, which is moles per liter, times volume, this would have to be liters. But if you leave this in milliliters and the other volume in milliliters down the line, then they cancel each other out. So that works out fine. Now, what volume is that? Well, that's just what you're dispensing. The 1 mil, the 1.15, the 1.25. Now, I'm not going to fill out all of this for you. So that'll give us molarity times volume is moles. You've seen that lots of times. Now you multiply by your, however you want to look at it, your mole ratios. I'll let you figure that out. Actually, if you think about it, it's HCl, monoprotic strong acid, and dibasic carbonate. So that should give you some clues on how to use the mole ratio. Then you multiply by 1 over the volume of the HCl. Now here's this little trick though. When you have all those volumes of HCl from that table, what are we talking about here? That's the total volume. The volume it took to get to the first equivalence point, endpoint, plus the volume it took to get to the second equivalence point, endpoint. So it's the total volume of HCl it took to do that whole set of data collection. So molarity times volume of your standard, your mole ratios, divide by the volume of the HCl, and you should get an answer close to around 0.1. And depending on how you record data, you should get 3 or 4 sig figs. Then you do that all 3 times, and then you have an average molarity of HCl. And that's where we're going to end here. So you should have your final answer for molarity of HCl should be about 0.1. Everything else beyond that is doing all the ICE table calculations, which we'll pick up there in lab. So I hope that helps.